All right. The alkyne chapter is really similar to the addition of alkenes chapter. A lot of the reactions look very similar reagents. I do want you at home to study acid-base chemistry on your own. It's really similar to last term. And I also want you to study nomenclature at home, meaning naming. The naming is really similar to the naming for alkenes. What do you guys think the difference is going to be? The suffix, right? It goes from ene to yne. Really, that's the big takeaway from that whole section, so I'm not going to waste class time on it. All right, so now we need to talk a little bit about how to prepare alkynes, and so let's jump into that. So preparation of alkynes. It's pretty similar to preparation of alkenes, but one extra step. So let's briefly review alkene preparation. Sorry. So how did we prepare alkenes in the last chapter? So let's say I've got this compound where I've got a halogen coming off here, and I want to make this into styrene, which contains a double bond in it. What should I use? What reagent would be appropriate? Probably some sort of base, right? In this case, it doesn't matter whether it's large or small because you only get one product. So in this case, I'll just write generic B with a negative charge, and we can do an E2 elimination reaction really easily on this because we do have beta protons. Specifically, we've got beta protons coming off this end right here, right? So standard E2 chemistry can be used to give an alkene, but let's take a look at alkynes. What do you think we would do if we wanted to make the same molecule, but instead of a double bond coming off the end, we want a triple bond? Does anybody have an idea? What if we just do it twice? What if we have two halogens and do two E2s, right? So let's take a look at what that might look like. So we've got a bromine here, bromine here. Same sort of thing. We've got beta protons over here. They're on the carbon next door to each of those bromines. I can have some sort of base with a negative charge. Typically, this base is going to be a really, really, really strong base, though, because we want to encourage formation of the alkyne. So I'll grab one of these protons. We'll clamp down, kick off our bromine. We'll make our alkene first. So we'll still have a bromine coming off here. And then in step 2, we'll use another equivalent of our strong base. This base will grab the second beta proton, clamp down, and kick off your bromine. Now we've got an alkyne. Specifically, it's a terminal alkyne, meaning it's not in between two carbons, it's only attached to one carbon. I did want to introduce a few terms, though. This type of dihalide that we start out with is called a geminal dihalide.
Why would it be?
A geminal dihalide means both of the halogens are coming off the same carbon. We will see an example later where you can have halides that are next door to one another, and those are called vicinal dihalides, and those are different. Typically, in these reactions, though, you are treating it with a very, very strong base and excess. So what do you think happens? Actually, I'm going to change color of this pen. If we've got excess base around, what do you think it can do?
Do something to the proton on the right.
Yeah, it can pluck off that last proton. If you remember back to first term, I said that alkynes are unusually acidic, and why is that? Because of the orbitals, right? They're on an sp orbital, and we said sp orbitals because they're so short and stubby. They're actually pretty stable as a conjugate base. So if you have any excess base around, it will immediately grab this proton and deprotonate it. So it's hard to control. And you'll end up with this ion. This is referred to as our acetylide ion. it's almost unavoidable in this reaction. You typically overshoot and get the acetylide ion. So what most chemists do as their workup is they treat this with some water. And water is cheap, it's abundant, and it will donate the proton back to that alkyne in order to give you your neutral product. So let's make a note of that. Typically, your base is used in excess. So you must reprotonate with a weak acid. It's not uncommon to see this throughout the chapter, so I did want to kind of briefly explain why. Does that make sense? The pKa of these alkynes, the terminal alkynes, are typically around 24, so they're not super acidic, but they are relatively acidic compared to most hydrocarbons. If we think about an alkane, the pKa of an alkane is about 50, so we're talking about 25 orders of magnitude more acidic than a normal hydrocarbon. So it's a lot more acidic than a normal alkane. The alternate route, and I'll show you guys this really quick, is pretty similar, so I'll do a big OR. You can have both halogens coming off of separate carbons. Again, we'll treat this with a strong base. That would be step 1, and I'll just write excess. And then step 2, we'll treat this with water. And when you do this, just like before, you can do a double elimination reaction in order to give you your terminal alkyne. And so this is a little bit different than the reaction we saw before. The only difference, though, is this time we are using a vicinal dihalide. Does that make sense? Because each of the halogens does have beta protons, so an E2 can occur for either of those halogens. I did want to show you guys the base that's commonly used. All right, so a commonly used base for this reaction is going to be NaNH2, which is also known as sodium amide. So quite often in this chapter, you will see this as the strong base of choice that Klein uses. So think of it as any generic strong base, but this is the commonly used one. Does that make sense? All right, so now we're going to jump into the first reaction of alkynes, and we'll see that a lot of these are really familiar. We'll do reduction, and we'll compare and contrast this. Let's say I've got this alkene, and I want to convert it to an alkane. What should I use? Hydrogenation. So we need H2 gas. What would be a good catalyst to use? Palladium on carbon, something like that. So all right, just PD/C. You can use platinum. You can use Wilkinson's catalyst. Pick whichever one you want. So it's pretty common for alkenes to hydrogenate them. You're going to add the hydrogen syn or anti? Syn. But in this case, it doesn't matter. We're not forming stereocenters, so I'm not even going to bother showing it. Let's take a look at alkynes. With alkynes, you can do a similar thing. So let's say I've got the analogous alkyne, and I treat this with H2 and palladium on carbon. A lot of people would say, well, all right, what if we add two hydrogens syn to one another? Shouldn't this be our product? The problem is it can't stop here very readily. Instead, it will overshoot, because normally when you do this reaction, you're doing it in a high-pressure cylinder full of hydrogen, so it's got a ton of hydrogen around. And so if there's excess around, it will just immediately overshoot and go all the way to the alkyne. So you can't observe this. you always go from your alkyne with the triple bond all the way to the alkane, meaning straight to your single bond. So let's make a note. Typical hydrogenation will overshoot and go directly to your alkane. Chemists really don't like being told they can't do something, though, so a lot of chemists try to figure out a way to stop at the alkene, because there may be some reactions where you exclusively want that alkene intermediate. So let's take a look at the tricks that chemists developed for stopping at the alkene. Specifically, they developed a new type of catalyst system, and these catalysts are called poisoned catalysts. And I'll show you a handful of the poisoned catalysts here. The first one is referred to as Lindlar's catalyst. And typically in the Klein textbook and in Sapling, they'll just say Lindlar's catalyst. They won't even write out what's in it because it's so absurdly complicated. But I'll just show you for fun. You don't need to memorize this. I'm just showing it to you. So you start out with a ligand. It's a nitrogen heterocycle. And then you have this palladium barium sulfate mixture. And typically this is done in methanol. We're not even going to get into the why behind this, but essentially it's not reactive enough to overshoot. It's a little bit more sluggish, so it can stop at the alkene and it won't go any further after that. There's a second one that's called the P2 catalyst. And you use hydrogen gas in this one. And really this is a nickel-boron complex. So it's 2 nickels for every 1 boron. But typically, just like with Lindlar's, people will just write H2 plus P2 catalyst to indicate that these are poison catalysts. So let's take a look at some of these examples. So let's say we take that previous internal alkyne that we had before, and this time I'm going to take hydrogen gas and Lindlar's catalyst. When you do this, you're always going to get syn addition of 2 hydrogens. So does that mean we're going to get a cis alkene or a trans alkene? Yeah, exactly. You always get your cis. It's a pretty clever trick that they came up with, specifically because we know that cis alkenes are more prevalent in nature. We mentioned yesterday with fatty acids that trans alkenes or trans fats are bad for you. Nature really prefers to make cis alkenes. All right, but then the question is, well, what if we do want a trans alkene? What tricks can we pull out then? Not quite. So we're going to use dissolving metal reduction. This reaction is a lot more hazardous to carry out. You don't typically see a lot of chemistry labs doing this unless they absolutely have to, and I'll show you why. Let's take that same alkyne, but this time we want to make our trans alkene where we've got our hydrogens coming off opposite sides. So I'll say only trans alkenes. In order to make this, you have to get elemental sodium. What's the problem with using elemental sodium? Does anybody know? super reactive. It'll react with water and actually kind of fizzle and make a flame. So it's very, very reactive. And then the other thing you use is ammonia, specifically liquid ammonia. This isn't your standard cleaning ammonia that you use at home. The problem with using liquid ammonia is it is super nasty to work with. If you spill it on yourself, it'll start eating away at your flesh. It's not something you want to have an accident with. So most labs prefer to avoid this if possible, but you do see it a lot in these classic chemistry textbooks. Yep. Household ammonia is ammonia that's bubbled in with water, so it's very, very low concentration. This is pure ammonia, meaning no water. So that's a good question. So oftentimes organic chemists in particular, to indicate that something's elemental, they'll write a little not sign above there to differentiate it from sodium as an ion, right? So it's not Na+, it's sodium as a metal. So people often differentiate it because of that. So let's make a really, really brief reaction map showing our hydrogenation pathways or reduction pathways. It's pretty straightforward. We said we can have an alkyne go all the way to an alkane. And what reagents do we need again? Let me shorten this up. If I want to go from an alkyne to an alkane. Just our standard one, right? So we can use hydrogen gas and palladium on carbon, right? And then we said we can also favor cis alkenes where both of the hydrogens are coming off the same face. What reagents do we need to go from an alkyne to a cis alkene? We need H2 and which catalyst? Lindlar's. All right, and then alternatively, we said we can go to a trans alkene where the hydrogens are installed on opposite faces. And what do we need for that? Yeah, elemental sodium and liquid ammonia. And then what if I want to go from either of these alkenes to the alkanes? Yeah, just H2 and palladium on carbon. One thing we will get into a little bit later is the reaction mechanism for the dissolving metal reduction. However, it involves a radical pathway. Specifically, it involves an anion radical intermediate. And so it's a little beyond what we've seen because I haven't even shown you guys what a radical is yet. So we're going to hold off on that reaction pathway until we get to that chapter. We have about 5 minutes extra. So what I want you guys to do is to try working on your pod and try to work backwards through it and say, all right, I know the product I need to make. How can I make that product given the reactions that I know? And try to use the recently covered reactions.